1, 2.
Okay. Okay, cool. Welcome to our panel on formal verification. I thought we would start by just introducing ourselves, and then get into some questions we're going to answer, and then we'll ask for questions from you guys. Great. So my name is Derek Sorensen. I am working with PowerFX on the formal semantics of Rolang. So I'm working a lot in K-framework. We won't be talking about that today. There's a talk tomorrow about that. Instead, we will be talking a lot about what these guys are doing.
Hi, I'm Livnev. I'm working on smart contract formal verification research at DAPHub.
I'm Martin Lundfall, and I'm also working with Lev on this. And I think it is worth mentioning that the formal verification we've been doing has been mainly focusing on Ethereum smart contracts. So it's worth keeping that in mind if we mention something specific about our smart contracts. But many of the methods that we've been using can easily be carried over to verify other smart contracts, and in particular the ones we're going to be working with written in Rolang.
Cool. Yeah, as far as I understand, a lot of these tools that have been developed to formally verify smart contracts can be sort of transported. So I think most of what we talk about today, the vast majority, is going to be what we hope to do with Rolang smart contracts in the future. Sort of just to give you guys an idea of what's going on and how we're going to do it, and yeah.
It's also worth mentioning. So at DAPHub, this results we present our joint work with Dennis Erfurt, another researcher at DAPHub, and the practical work that we're doing is building on the K framework, which is developed by teams at Runtime Verification and the University of Illinois and a few other academic institutions.
Great. Okay, so the first question we probably should ask to either of you is, so yeah, let's start. What is formal verification? Why do we do it? Why do we want to do it?
Sure. So formal verification is a process of in mathematical rigor specifying the behavior of some program that we intend to write or are writing, and then describe the language in which we are writing this program in mathematical terms as well, so that we can analyze the behavior of the program that we have written and compare it to the specification, so the formal definition of what the program should do, and see that we have actually achieved our goal. And most often, when we are actually writing programs, or in most programming, people tend to sort of overlook the aspect of writing the specification. And this is often a fairly hard part, if not the hardest part of doing formal verification. It's actually coming up with a good definition of what your program should do. And then once you've really realized this and are able to describe it in precise mathematical terms, then verifying that your program does this becomes a slightly easier task. And I think the reasons why we should do this is fairly obvious to anybody that has been following the blockchain space and seen the catastrophes that have sort of come from various bugs in smart contracts due to failures of actually writing correct programs. And in the blockchain space, these become very costly, and obviously we don't want to lose millions of dollars worth of assets due to some failure that could be detected by doing formal verification. So that's really the main motivation, to make sure that we actually deliver what we advertise that we're delivering when we're writing these smart contracts that are so critical in terms the money involved. And so formal verification sort of goes along, historically at least, two main lines where one facet is being driven by a sort of dependent type oriented setting, or a functional programming oriented setting, where you get a lot of the actual specification of your program in the typing of your program. And then if you manage to inhabit your types with terms, if you have a rigorous enough typing system, you're able to actually, by construction, know that your program intends the way that you want, because this information is captured in the typing information. And in this other branch of formal verification, historically it's been mainly oriented around imperative languages, where you describe the behavior that you intend your programs to have by pre and post conditions. And your claim is that for all programs that match this precondition, I will eventually reach this post condition. And our work is mainly along the second branch of formal verification, following with the pre and post conditions. And this is a branch that is also a lot more amenable to automated tools that can find you these proofs that actually show that your programs do what they intend to, and satisfy the reachability claims of pre and post states.
Cool. Awesome. We're actually going to see a demo in a few minutes of a proof along those lines. Great, thank you. Okay, so this may be obvious to some people here, but for many, as we've experienced it, for many, this is not a clear question. So we definitely want to address the following. Okay, so Lev, how is formal verification different from testing or from static analysis?
Right. So there's a few useful techniques that everyone in software development knows about, like testing. So testing is simply running your program on some concrete instance. So initialize with some concrete values that you came up with, either because it's kind of a happy path, like it's some values you actually expect your users to input, or because you're actually manually trying to find edge cases. So you wrote some program and you're afraid that it might suffer from like arithmetic overflow. So you'll give it some really nasty numbers, hoping that to see whether or not this will trigger an overflow. This is a very good process, and everyone should obviously do this. And in fact, almost everyone is using testing. But the kind of the theoretical problem with relying only on testing is, with testing you're only checking one of either a huge number or possibly an infinite number of executions, and you're not ever going to check exhaustively the whole space unless you're in some very exotic setting where the whole space is very constrained. A simple analogy would be that some of these formal methods you can view them as testing with all possible values. So there's this idea called symbolic execution, which is kind of like simulating the execution of a program where your inputs are symbolic. So instead of testing what this function does on the values 2 and 3, I'll test what it does on x and y. And but if we take this kind of precondition postcondition perspective, we might impose some preconditions on x and y and see what happens in the end. We might apply some other preconditions and so on. So it's actually really similar to testing, because often when you're writing tests for a computer program, you initialize your program with some values, but they're concrete values that you chose, and then in the end you check stuff like did it throw, did it change state, how did it change state, and you get a check mark like, okay, this behavior was fine. But you could compare it. So I think what we're doing is the kind of slogan for it is testing across symbolic values, testing across all values. And this is much more challenging than just typing in x and y into your environment, because to execute a program symbolically in full generality, you need to have a very solid grasp of the semantics of the language that you wouldn't get just from an implementation. Like this? Okay. Try next time.
Thank you. So another way to think about this is normally with testing, you take a sample of cases, and you may construct these particularly to to be as nasty as you can, or if you really don't know where your problems might lie, you might try to take, some sort of quasi-random sample. And with statistics, we take a sample of our population, we analyze the sample, and then we try to infer things about our population, but we always deal with some uncertainty. With smart contracts, we don't want to have any uncertainty, and so the point of formal verification is not to take a sample of cases and test them, but to test all cases all at once. And that way you get like a full mathematical proof, and not just this is most likely probably true.
Yeah, it's especially in the adversarial setting, which we would see with high-value, crypto, financial applications. There's no reason to assume that your random selection of test cases are representative of the real distribution in the wild, because your wild samples will be selected by an adversary who'll be trying to break it. Having said that, there are a lot of more interesting testing approaches like quick check and fuzzing, where you can actually select a huge number of random test cases using some kind of intelligent heuristic that will try to explore as many different paths in the program. And people have done quite interesting work, and often you will actually, it'll be helpful, you'll find something. But even then, unless you're actually doing an exhaustive search, you're really relying on heuristics rather than formal guarantees.
Great. Awesome. Thank you. Okay, so let's talk about the kinds of things we can prove or expect to prove with formal verification. So I'll hand this question to you, Martin. What properties can we expect to prove from smart contracts? And if possible, can you give examples?
Yeah, I think a good first answer to that question is anything that we can specify, we can formally prove or disprove. So as long as our specification is detailed enough that it actually outlines the behavior that completely determines our program, then we can check for that behavior using formal tools, and we can see that it actually matches the spec. But especially in constructing crypto-economic protocols or smart contracts, the types of correctness behavior that we're after can be a little bit trickier to define, and are actually most of the time reliant on game theoretic properties and reasoning about incentives that are harder to do in the formal verification setting. With the work that we have been doing, initially we've been mainly looking, for example, at one transaction at a time, and see what can happen in our contract within the course of one call to the contract. And even in doing this, we can see a lot of things and improve a lot of properties. For example, since the majority of the variables in our protocol are abstracted away, we can say that it doesn't matter what has happened before this transaction, as long as my program is in any of these states, I will be able to execute this. So in that setting, we don't really have to care much about what happened before or what will happen after, because we have abstracted those features away. And then you can say, for example, there's no way that my contract is going to get stuck, because if I've shown by looking at all of the functions of my contract that there is nothing that increases some array to an enormous size or changes any of the code, then I can be sure that those invariants will hold by simply looking at all of the possible methods that are available and making a conclusion based on that. So I guess mainly those are the easy properties to verify, that that the behavior from a particular call to the contract is according to the specification. Some slightly more non-trivial properties that we have some ideas on how to approach, but haven't really gotten to the stage yet, is, for example, reasoning about replay protection. If you have some contract that, for example, verifies signatures and does some action accordingly, what would happen if somebody submits the same message multiple times? because that would be a property that you would need to reason about over the course of more than one transaction. And also, if you have a problem space where it's important to reason about minor front running, for example, or really any other aspect of your contracts that involve sort of the business logic or the incentive reasoning, is more difficult to do because you need to take more than one transactions into account.
So how do we deal with loops in a code, or suppose we don't know if a contract will halt? Can you talk about that for a little bit?
Yeah, there's a very powerful technique at hand, and it goes under the name of co-induction, which is a general proof methodology in mathematics for reasoning about infinite structures. And as the name suggests, it is closely related to induction. If you want to understand it from a category theoretic perspective, it is the dual, where induction is understood as a special case of a initial algebra of an endofunctor. Then co-induction is understood as a final co-algebra of an endofunctor. And if that means something to you, then that's great. If it doesn't, then another way to think about co-induction is, whereas induction says that something is true if there's a good reason for it to be true, one can describe co-induction as something being true if there is no good reason for it not to be true, or sort of an induction without a base. And so what that means in the context of verifying programs with loops in them, then co-induction provides you with a mechanism by which you can sort of bypass a loop. You can have a co-inductive hypothesis that tells you what you expect the behavior of the loop to be. And as you go to the loop head, you're not allowed to initially use the co-inductive hypothesis, because then you would be able to prove everything and it would be trivial. So the nature of a co-inductive hypothesis is that you can only use it after you've made some progress in your proof. So in the context of a loop, you would go to your loop head and you would step through the loop once, and you would get to another state at the loop head that would still match the preconditions of your co-inductive hypothesis. And since you've now made progress in in constructing your proof, you can apply the co-inductive hypothesis, and you reach some state out of the loop. And the only thing remaining in order to prove the whole conjunction, or sorry, to prove the whole behavior of this loop, is to now show that the state that you have reached after applying the co-inductive hypothesis is implying or will rewrite to the state that you would get if you initially applied your co-inductive hypothesis. And if there was a whiteboard, I could draw this in more detail. But in lack of that, I think I'll leave it at that, and I can recommend some resources if people are interested in that. But basically, in the branch of formal verification that deals with infinite structures like loops, or when our execution tree has these loops in them, where we can't be sure of how many laps around the loop we will do, then this becomes a very powerful tool.
Cool, thank you. Yeah, Martin has quite a bit of experience in this area, so if you are interested, please talk to him after we're done here. Lev, this question is for you. How does formal verification inform the development process of smart contracts?
Right, so I mean, we found it actually really helpful to link up the formal verification research and the actual development of the contracts that are the targets for formal verification by having very frequent feedback going both ways about the developers discussing what features they're planning to add and how they're planning to implement them in full detail. And then if you're whoever's working on actually formally verifying them will you know, say how they plan to do that. And actually this turns out to be a really fruitful thing, because when you've been working with a contract that you're trying to formally verify for a long time, you start to get a really intimate understanding of it that you know, sometimes even the person who was writing it originally doesn't fully appreciate. So you can, I mean, to be specific, we've been working on formally verifying the system smart contracts for a system called multi-collateral DAI, which is a really important piece of financial infrastructure on Ethereum. And this we were working on this for a very long time, and eventually we kind of arrived at a few, you know, really valuable lessons for the development process. So things like, you know, if you want to have a certain core of your contract, which you want to have like especially sound security guarantees, then, like, you know, you should try to avoid calling out of this core into some less trusted contracts. So this turned out to, you know, be a really nice way to design things, and at this point, you know, this greatly strengthened the claims that we could make on the formal verification side. If we're not calling into code that's not been formally verified, we can do a lot better. Also, things like how to do math safely. You know, this is supposed to be very very simple, but when you're doing a lot of arithmetic, there are different ways of checking for overflow and different choices that you can make, whether you want to use what type of integers you want to use and sizes, and how you want to store them, and how you want to store them to save, to be more efficient in storage and pack them together and things like that. We kind of came up with a lot of ideas jointly together with the developers and how to do that safely, because, you know, we can kind of get a lot of confidence when you have some idea of how to implement, you know, safe arithmetic. You can just throw it into the stuff that we're working on and get some proofs, and then you can actually, you know, tell people that this is definitely a safe way of implementing arithmetic, rather than having to rely on, like, kind of conventional wisdom only.
Thank you.
It can also be quite interesting to discover bugs in compilers, since what we're doing when we're doing formal verification is that we're looking at the compiled code and see whether it matches some specification, whether the specification is, of course, informed by looking at the code in the source language and the understanding of how this should act. But the target of the specification is always the outputted binary or the compiled code, and then it becomes a process by which you can discover quirks in compilation, which happens quite a lot. Questions? Yeah.
Can I ask a question about verification of Ethereum smart contracts? So my question is, I'd like to know some example correctness properties that you have been verifying. So the background to my question is the following. It seems that it is important to, when reasoning about smart card computation, it seems to be, it's important to view these computations in a distributed computing environment. There was a recent paper published at CCS by a bunch of security researchers who showed that it is important to take the semantics of smart contracts as distributed programs seriously, because by exploiting, I guess, the lack of clarity in the specification of the semantics of smart contracts, they are able to, in fact, introduce new security properties and show that there are many smart contracts out there which fail these properties, and they have been able to identify known bugs using this approach. So, I mean, you mentioned earlier that you have taken the approach of pre and post condition. Do you do this in a sequential deterministic setting, or do you do this in a global distributed computing scenario?
So for Ethereum, we are a little fortunate in that some of those issues aren't issues because we always force transactions to be serialized. So given any block, we always know the order in which transactions will be executed. So we don't have those non-deterministic issues that can arise from not knowing in which order two transactions will be. So there is still the problem where, as somebody calling a contract, you don't know what state the contract will be in when you're making the call, because some transaction might slide in before you. And so those properties belong to the category that I mentioned before, where we're not quite at that stage where we're able to reason about several transactions in a row and the properties that come from their various orderings. Mainly what we've been doing right now is what can happen during the course of one transaction. But with the tools given by the K-framework, it's not infeasible at all that we would get to this stage fairly quickly, because this sort of takes the first step towards that, in the sense that what we're doing is now building from all of the minute steps of the Ethereum virtual machine. We're building sort of a big step semantics of the program, where we can think of all of the calls to the various functions that we have as being atomic. And we don't have to care about the intermediate virtual machine states. And then once we have those sort of big step semantics of contracts, we can start reasoning about what happens when you compose them in different ways. And of course, when it comes to the sender of various transactions, this is abstracted away. So we don't have to worry about any issues arising from authentication issues, because this is another variable that is abstracted away in the pre and post conditions.
I think so. I think Martin did a good job of stressing how our current approach is to really consider the pre and post conditions, beginning at the start of a call and then ending at the end of the call. I think to give a worthier answer to your question, it would be good to consider like some examples of situations where the semantics is affected by the distributed setting. I don't want to make too strong a statement, but kind of at the level of specifications that we're working with right now, this is these transactions are serialized, and we are in a kind of very deterministic, non-distributed setting actually.
Yeah, I mean, thanks for the clarification. I think it's entirely reasonable to be upfront and be clear about the assumptions. Otherwise, the verification tasks may be impossible. But I think the paper that I referred to is in a distributed setting, and it in fact exploits, so they manipulate ordering between transactions, or between atomic steps of the transaction. And they claim that they do this while observing the specification of the semantics.
Yeah. So for example, I'd like to stress that our specification would never say something like, the caller receives an integer randomly, uniformly chosen from some interval. So for example, you can easily build you can kind of naively build some protocols for getting random numbers on the blockchain, and then it turns out that if other participants in the network or the miner might choose to withhold a block, or might choose to prioritize certain blocks depending on their own agenda, then the number will not be random. Or similarly, as you mentioned with things like transaction signing. You might have forgotten to put in a nonce, and then some transaction could have been played twice. This kind of thing. But again, these things this would never kind of appear in the type of spec that we're working with, because we wouldn't make a claim like that. We would make a claim that only formally makes sense, within the scope of just one transaction.
Great, thank you for that question. I think the next natural question for us to ask and wonder about is, suppose I give you a smart contract and I say, I want you to formally verify this smart contract. What does that mean, and can you give us maybe a demo or something about the process that you go through when you do that?
Yeah, I think we could do a demo, but I'll start by, I think we've already touched on most of these points, but just to make it really explicit what the process looks like. So the first thing is you need semantics for the language that you're working in. So the verification will only be as good as the semantics. Now the semantics can't really ever be, what you want in the end is you want the network, so let's say we're in the blockchain setting, but whatever, the clients, the computers that are executing your program, you want them to execute the program in the way that you expected. So your semantics has to correctly model their implementations. Maybe in the future, people will actually be running the semantics as their implementation in some way, and then you'll actually have a guarantee that you're running the same thing. I mean, up to the implementation of the semantics itself. But today there are actual implementations of nodes that might not be the same as the semantics. So the first thing is that your proofs will only be as good as the semantics. And the next part is the specification for your contract itself. So we were discussing this a little bit earlier. So in our case, we're specifying kind of the pre and post conditions within a single call. And you've written that down. And really, my perspective on what a specification should look like is it will look like it's doing very, very little, and it's going to look very similar to the implementation itself. And that's because you're kind of, at this level, you're only trying to achieve one thing by writing a specification. That's moving from statements about some computer architecture, some virtual machine, to abstract mathematical statements. So a good specification would have minimal references to how the virtual machine works. You ideally shouldn't have any weird operations floating around, like addition that might overflow or bounded things. It should be a claim about integers. It should look like a mathematical proposition. And the reason is that in the end those are easier to reason about. So that's what people are actually thinking when they're reading code. Is they're simulating in their minds that they're working with integers, and in reality they never are. They're actually working with machine stuff. So a specification is only really supposed to make the small jump from implementation to abstract kind of implementation, the kind of platonic ideal of your program. And sometimes that will look really similar. I mean, it could look different. So for example, I might have an algorithm for multiplying, or let's say I have an algorithm for finding an inverse of a matrix or something. The specification can postulate that a method is doing that simply by claiming some matrix multiplication is the case, while the underlying implementation can be vastly more complicated because it's non-trivial to do this, but, even though it's easier to check it. But in some more trivial cases, it might actually look exactly the same. You might have a really similar specification implementation. The only difference is that you've replaced like machine integers, for example, with abstract integers, and you've replaced all these virtual machine level operations with kind of the real mathematical counterparts. So once you've got a specification, the goal is then to prove that some implementation that some developers have made agrees with it, so that you're basically combining those first two steps. You're taking the language semantics and you're combining it with the specification of this particular program, and showing that this kind of abstract execution of that program will satisfy the abstract claims you made in the specification.
Yeah, we can demo this, and the tool that we're now going to be showing you, as Lev said in the beginning, much of the work that we've been doing is building upon work that is developed by runtime verification and the people developing the K framework. So the tool that we're now going to demonstrate is called KLab, which is a graphical explorer of the underlying proof engine of the K framework. Because as we started working with the K framework, we found it a little bit of a black box where we couldn't really have any good heuristics for understanding why proofs went through or why they didn't go through. We developed this tool, mainly Dennis, that allows you to step through a K proof and see all of the execution paths that it explores, and figure out if there are extra lemmas needed and stuff like this. So maybe I think we can just run this. So this is a very simple program just to sort of illustrate the process. Actually, the program fits in 6 lines, and it's a very simple solidity contract that adds 2 numbers x and y together and simply checks that it doesn't overflow these 2 numbers. So we call it safe add. The specification of this program is what we have in the file called spec.ini. So what we see here on the left-hand side are various cells. These are like tiny parts of what's called a configuration in K. So tiny parts of the world that are relevant to our execution. And what we see on the left-hand side is our pre-state or precondition, and on the right-hand side we see our post-condition. So for the purpose of this program, we are, let's bring the program up in another file. Can you hold this microphone for a second?
I can try to provide commentary on what you're doing.
Yeah, can we get this mic working as well on the podium? Oh, great, thank you.
I can hold it for you.
So the Solidity smart contract is on the right here.
I think
just in
both
case somebody
microphones are working
forgot
right
it.
now. That one is working right now, I think.
This one?
Yeah.
Oh, wonderful. So the very simple clauses of our program is dealing with x and y now in capital letters that are actually now meta level integers. So they are real integers, integers considered by K, and not these words that we consider in the Ethereum virtual machine that can overflow and all of this nasty stuff. So similarly, this plus that we're considering here is a real integer plus, so it can't overflow either. And so the specification is simply saying that given a call to this add function with the integers x and y, under the condition that our x and y and x plus y are all within the accepted range of 2 to the 256 words, then on our output cell, we will be seeing x plus y. So very simple, tautological almost, and this is, of course, as intended. So when we run this program, it looks very similar in the beginning to running something in an EVM debugger like HEVM, but pretty soon we find that on the stack we have symbolic values, x and y. And this is something that is really hasn't really been possible before the development of these tools. So this is pretty exciting. And then as we step through the various steps of the program, we eventually reach the final state. And now the output cell isn't really displayed here, so
you can hit M to look at the memory.
Sorry?
You can maybe hit M to look at the memory.
I don't have...
Maybe it's an older version.
Yeah. I don't have that. But anyway, we see a little success banner in the right-hand side here, showing that our spec actually went through. So this is a very simple program, but if we were to consider something with a little bit more of exotic behavior, such as a contract that branches and explores multiple execution paths, we can actually see all of these paths. Looking at B shows the behavior of the program, and so here we're able to step through to the various branching points of our program and see the additional conditions that are added to our list of conditions if we were to explore this path. By running this tool on various programs, we are able to explore the complete behavior of smart contracts. And given a specification, we can see that they actually match it by exploring all possible execution paths.
So those green check marks, yeah, can you explain what those mean?
The green check mark means that in exploring this path, we reach the post condition, which is specified in our specification or in our proof claim. So we see that some of them instantly lead to the post condition that we have specified, and in some of them we need to explore new branches. So the longest branch here is the one that goes 1, 1, 1, 1, 1.
So each of those check marks corresponds to a branch, if I understood that right then.
You can sort of, so a checkpoint is a branch that ends in the specified post condition, yeah.
Great. Great, thank you. Do we have any questions? We've got about 15 minutes left for questions from the audience. If you want to ask a question, be sure to use the microphone, and Kelly will help us there.
So in theory, there are some results that verification in general is not possible, for example, because of the halting problem. Like, what implication does it have in practice? Like, of course, I can say in a smart contract, I just have a finite number of iterations because I will run out of gas. So in theory, I could always verify smart contracts, but like, what are the real hard cases maybe for practical verification?
Yeah, so I mean there are many things that we can't provide any guarantees about whatsoever, and a very simple example I think is a multi-sig where you allow an execution of an arbitrary transaction. So if you do if you have a multi-sig where you need to gather a sufficient amount of signatures before you execute something, then of course, since this execution itself will be completely abstracted away, then you can't say anything about the transaction. And this is sort of fairly reasonable, but these become problematic when we're doing sort of blind calls in a contract. If we have a application that does a call into a contract that we don't know beforehand what it is, then we can't say anything about that call. So the more you have abstracted away in your contract, the less we can say about it.
Yeah, I would say that also. So intuitively, I think the situations where you face difficulties maybe have little to do with the inherent difficulty that comes from the kind of halting problem argument. So because we're not we're only trying to verify specific contracts that someone might actually conceivably want to use, rather than some like some pathological program that someone might create for such an argument. Clearly, like the computational properties of verifying arbitrary things automatically don't look favorable. But to add another example of things that are difficult to reason about, which is related to this calls issue, is that, for example, in a lot of things, it's actually really important to, somewhere in your execution, to call some unknown contract. Like ideally, you wouldn't be calling if you didn't need to, but for example, one of the quirks about Ethereum is that if you want to send some ether to some address, you actually need to call it. So for example, that's kind of the idiomatic way that Solidity would implement this. So you've been given such a thing to verify. You will then have to somehow work your way around this, but what's happening is that your contract is making a call out to some unknown thing, which will have code, which will probably execute. You have a few things in your toolbox, which is that the amount of gas that was forwarded into this call is bounded. So in theory, you would only need to explore some relatively small number of potential execution steps, but that's not much of a relief because it's still like 2,500 gas, and a lot of things could happen in that time. So you might need to resort to some meta arguments where you say, I don't know what will happen in this period of the execution, but because of some property of the original contract that I was verifying, it's okay. So for example, if your original contract has a lock to prevent reentrancy type attacks, then you'll say that, okay, well, at least the state of this of this contract itself will not be modified because it cannot be entered. Because look, all of our other specifications for this contract say that when the lock is locked, nothing can change. So that is a meta argument that you have to make, but it's actually fairly persuasive and might be one of the only things that you can do in that situation, or just not avoid doing a call.
Thank you. Next question.
Thank you. Thanks for your talk. You were telling that you're not using the type system yet in your formal verification, but this is something going to be big in our chain with the. So maybe you can tell me how you are going to go to the dynamic typing and the formal verification.
Yeah. Do you want to talk about this, Derek?
I can talk about our plans for type system with rolling, but I think you may be able to address the issue in a broader level.
I'm not sure I can, but it sort of depends on what precisely you mean by typing, because in a sense the verification that we are doing is very much a sort of runtime exploration of the complete state space of a program, and you could make types out of those claims. Like you could say, for example, every function that ends with this particular behavior, I'm going to assign this particular type. But you do get the sort of nasty property that type checking would be much more computationally expensive than running the program itself, which is something that a lot of computer scientists are sort of upset with, or at least regard as an undesirable property of a typing system. They want type checking to be at least faster than execution. So in designing typing systems, this is something that you sort of need to keep in mind, that you want to be aware of the complexity of type checking, and want to make sure maybe that the properties that you're interested in verifying and ensuring with your typing systems are ones that are reasonably checkable within a certain period of time.
Yeah.
I just wanted to add a naive kind of comment that's fairly obvious probably, but So I mean, it's quite nice when you can check things statically, like with types, and that's why everyone knows that languages that have nice types are really nice to use, and people make fewer bugs typically, and so on. Unless your types are strong enough to actually express the properties that you would think are a satisfactory list of properties that would claim that the program is kind of verified to the greatest possible extent. So unless, for example, for which you might need something as strong as dependent types, then it will just be a kind of static analysis helping tool, which is not as deep-reaching as runtime analysis, which is the kind of thing that we're talking about, I think. So I think basically, this is echoing what Martin is saying, but in other words, is that your type system might need to be really powerful to get the same level of guarantees, and that might be undesirable for other reasons.
Yeah, and this is a question that I'll get to in just one second. This is a question that is an active sort of on our minds with Rolang. And in fact, Kyle in the back may be able to give more information on this. But in some sense, Rolang does have some built-in notion of types and sort of maybe a very weak notion of type safety in that pattern matching on channels. When you listen for a certain pattern on a channel, then you are sort of restricting the type that you're willing to receive. And it's sort of implicitly anything that is sent, although you may not declare some specific type, it sort of has some notion. I think this will play an important role. Kyle, yeah.
So for code that is high value and run in an environment that is trusted, do you think that the constraint where type checking has to be faster still matters? Because you can run the type checker in a different environment. So for example, on Ethereum, that constraint doesn't really even make sense because you can run the type checking locally and then you can run before the contract runs in Ethereum. And so like they aren't even something that you can compare anymore. It makes much more sense to have that comparison for local code. I was just wondering what you thought about that.
I mean, but also, before you can run the type checking on your laptop, you have to run it in your brain, and a lot of people find that to be a lot of overhead to actually formulate complex properties of their program using types. So maybe that's where the computational bottleneck is.
Yeah, we have a question right here.
So since programmers spend a lot of effort creating tests, do you think some of that effort would be better spent on formal verification, or do you think that formal verification takes so much time that it's only worthwhile for, I guess, high security systems type things?
Kind of our battle right now is to all this time that we've been working on this research for years. Our battle right now is to try to do as much work as possible, which will actually reduce the amount of work that we needed to do formal verification in the future. And maybe this sounds too utopian, but I'm actually hoping that, firstly, these types of interactive tools that we just demoed will become part of the toolkit that a developer uses alongside testing, or maybe instead of testing in some cases, even if they're not arriving at complete specs that are the standard that we call formal verification. So basically, the fact that you can run a debugger with symbolic values, you don't need a spec for that, is already pretty useful because, usually it's debugging a program. It's sometimes a little annoying that you have to choose concrete values and you don't cover the whole execution tree. But to go further, I actually hope that if we, in particular contexts where we have access to good semantics and we've figured out good kind of tooling and development practices that make your programs particularly conducive to this, that we can actually make it kind of accessible to just like the same kind of situation where you would do testing, right? So anywhere where you think that it makes sense to spend a couple of days writing tests, you might decide that it's worth spending a couple of days writing specs. I believe in that, but it's maybe sounds today crazy because no one seems to have ever done that, but I believe it.
Well, I think would be something worth exploring because tests don't seem very effective to me, where especially it's usually the programmer who wrote the code writing the test, so they're sort of writing cases that they anticipate to be much more effective to verify it rather than do some testing.
Yeah, we're sort of inherently blind to the errors of our own programs, so I completely agree with you. Yeah, it seems to be the mission of sort of started with K framework of making it easy. Grigory Rochu, he has sort of these introductory videos on the K framework, and he says, in the past it's been too expensive and too boring to define formal semantics for a programming language, and then he gives some examples about why that's a problem, and then one of the main points of his tool is to this K framework is to make semantics, he says it's supposed to be fun and interactive, and he even incorporated colors into the process, and so you can sort of make your semantics colorful, and then as we move forward, we get tools like KLab that really do a lot of the work for you that you would have had to have done yourself.
Yeah, just to show K framework a little bit, I would say it's a really good idea that they decided that instead of following this approach of defining ad hoc semantics for every particular language that you want to work in your favorite proof assistant or whatever, they focused from the beginning on developing a general framework which will accept different semantics and then reuse as much as possible in the kind of symbolic execution and proof search parts of the framework across different semantics. So this has saved, I think, already huge amounts of resources and made it practical to do things that you wouldn't have done before.
And this is also another reason why the work that we've been doing is gonna carry over a lot if one were to pursue developing formal verification tools for Rolang, because the main aspects that have made this tool possible and has made all of our work be getting to this stage at a relatively quick pace is that we have had this formal specification of Ethereum semantics developed by runtime verification in the K framework, and this is what Derek has been working on now to develop the formal semantics of Rolang in the K framework. And then this K-prover tool that comes with KLab and the KLab, the K-prover tool that comes with the K framework and the KLab tool that we have developed to explore those proofs are already generic enough that they take the formal semantics of a language as part of the input, and they are in fact parametric in the language that you're writing your programs in. And then just a matter of displaying things nicely depending on the particular aspects of the programming environment that are interesting to you. You would need to tweak those and make it relevant to your domain, but all of the back end is very much the same.
Cool, thank you so much. Thanks for coming. Thanks for being here. Unfortunately, we're out of time, so we're going to go ahead and end here, unless we have any final. We're good? Cool. Thank you so much for coming.